So previously we talked about the instrumentation, and we said that what we will be using is an automated polarimeter. Makes it much easier, makes it life much easier for you at least, as far as the readouts go. But these things are pretty pricey. You're looking at $14,000 to $16,000 for a polarimeter. So many people don't have the extra money to purchase a polarimeter like this, but we use it kind of often. So we can justify it and say we need an automated polarimeter instead of something that looks like this, which is what you would see in a traditional undergraduate chemistry course or laboratory course. Okay, so now we need to talk a little bit about the lab, and we need to discuss what we're going to be doing and what the purpose is, and what the whole theory and how this is going to relate to a polarimeter. So first off, what you have to understand is that in this laboratory, you're going to be using some sugars, and those sugars are a group of different sugars that are probably going to be 3 or 4 different ones that you're going to have to make and that you're going to have to analyze. So sugars are chiral compounds. And that basically means that they can rotate light, and they can rotate light left-handed or they can rotate light left-handed. And it's up to kind of us to figure out which way it rotates, and we're going to basically put it into a polarimeter and get some initial readouts. The thing, though, is that sugars are not simple compounds. Sugars are basically rings, and they're 6-membered rings. So I'm going to draw this sugar kind of as a ring, and one of the carbons is an oxygen in the sugar. And this is kind of how the molecule begins to start out. Now, there's groups that point up and down on each one of these carbons, but I'm not going to draw any of those. I don't want to complicate the screen on you by all means, but we need to talk about the basics of why this lab does what it does. So this molecule is a template of a sugar. And the problem is that this molecule can go from a ring and it can open up. And it can open up into a straight chain. So if it opens up into a straight chain, and again, there's still an oxygen on the inside here. So I'm going to draw this kind of here at the very end. And there's going to be some carbons here in the center. But it can go back and forth between this. Okay? It can go from a ring, which kind of locks it into position. And then it can open up into a chain. And that chain can then close itself back up and go back to the ring. And we constantly see this going back and forth, back and forth, back and forth when sugars go into solution. Okay, if sugars are not in solutions, then this doesn't have a chance to happen. You're not allowing the sugar to swim around in a swimming pool or into a hot tub. So it can't really open up and close itself back as a solid crystal. It really has to be dissolved, and it has to be in solution for this thing to work the way that it does. We call this phenomena Muta Rotation. Mutarotation. So muta means that it's kind of changing from its original form. It's a mutant, right? If you've ever watched the X-Men. So we're changing it slowly, and the molecule's changing slowly, but the structure's not changing. What's changing here is the rotation of the molecule. So the light energy is maybe getting bent more or bent less depending on the mutarotation and how it's happening. So sugars undergo this mutarotation, which means that if I make a sample of a sugar and I analyze it immediately, okay, so here, if I do it immediate and I analyze it, I would get a number from the polarimeter, and I can record that number down. All right. However, if I allow this sugar to maybe sit for 15 minutes and then I remeasure it, these numbers might be different. They'll be close, but they could be very different, depending on what kind of sugar that we have. All right. Well, if I allow that sugar can continue to sit and maybe measure it 1 hour later, I'm going to get another different number. Again, that number could be similar, but it will be different. Or it could be very different, depending on what the sugar is. Now, not all sugars mutarotate. So many sugars do, but here I'm going to put not all. Okay. Well, in this laboratory, you're going to have a set of sugars. Some of them might change, some of them might not change. And this is kind of one of the purposes of the lab. We want you to go through, we want you to analyze sugars, and we want you to determine if some of these mutarotate and which ones do not mutarotate, and kind of identify those in your laboratory procedure. You're also going to see a step as far as the timing goes that is listed in the lab procedure, but you're also going to see a step that's 24 hours later. All right, and you're going to have to do a number with that as well. So here's the issue that a lot of people have. You've got 4 sugars, and these sugars you're going to have to run when you make them at least 1 day later. And a lot of people think, oh no, I'm going to have to make 4 sugars and it takes a day to read each one. Then that means this is a 4 to 5 day laboratory, and it's not. Okay, and the reason that I say that is because if you're creative in your sample prep, what you would do is that you would make 1 sugar sample and you would run it immediately. Well, you've got some time in between before you have to run your next one at 15 minutes or whatever case that is. So during that time, make your second sugar and go ahead and immediately run it. And if you juggle your sugars that way, what you can do is you can run all 4 through the time intervals, back to back to back to back, and then have all 4 sit into the refrigerator after you're done, and then 1 day later go back and read all 4 of them again 24 hours later. And you can do this in 1 day. So you don't need 4 to 5 days. If you can't juggle the sample preps, and if you can't juggle making your sugar solutions that way, then you probably do need a whole week to do these one after another after another. But if you've got everything measured out, if you have everything ready to go, and the only thing that you have to do is add water to the volumetric flask, dilute it to the line, shake and dissolve, then there's no reason that you cannot run all 4 of them back to back like that. So you've got enough time in between to make those samples. You have enough time so they do not overlap with each other. You'll be perfectly okay. The next thing that I'll say is that it doesn't have to be 15 minutes exactly or 10 minutes exactly, whatever it tells you in the lab book. If you're 16 minutes instead of 15, no big deal. You just write that down in your lab notebook. Note that it was 16 minutes and not 15 minutes. That way that your graph will make sense when you get to that point eventually later on in the analysis part of the experiment. Okay, so mutarotation plays a very important part in chemistry. Some molecules, like sugars, will open up and close, and the reason that they change their rotation is because once they open up, the end, which is where the chirality is, can rotate. It's free to move. So because of that, when it closes back up, it might be slightly different position-wise than it was before it opened up. And that's why this happens. The open and closing allows this flexibility at the end of a chiral molecule or a chiral carbon. Here it's not going to be chiral because there's double bonds there, but you get the drift. All of these other carbons, many of them are chiral all the way down. Okay, so you'll get different readings. You might be surprised. Those readings will be different from the textbook, but the textbook is basically at equilibrium. So it's after the sample has been in the solution. This is traditionally the equilibrium rotation that you will find in a reference book. So if your initial readouts are not matching perfectly, no big deal. They might eventually get to that point 24 hours or 2 days later, depending on how the lab is written. Okay, so we can call this kinetics as well. How long does it take in order for it to flatline itself out? And that's going to be part of the analysis part of the lab itself as well. And we'll talk a little bit more about it later on. But that's the story with sugars. That's the story with mutarotation, and that's what's happening in the first part of this experiment. Your sugars are opening up, they're slightly twisting, they're closing back on themselves, and when they do that, the light rotation is going to slowly change on you. Different sugars It will come to equilibrium at different times. Some act quicker than others. Some never move. And it's up to you to figure out which one has the fastest kinetics, which one has the slowest kinetics, and which one never mutarotates at all. So again, you'll have a set of sugars in order to determine that. Okay, so in the next video, we'll continue on and maybe finish this thing up.